All right, so I got Einstein in an elevator here, and what you can't tell very well, I think, from the picture is that he's sitting on an old-timey, like a doctor's scale, you know? So there's a little reading right there that would be around at his belt buckle height, and he's standing on a platform, sitting in this elevator, and he's moving along. And one thing I want to keep in mind here is the idea of inertial reference frames versus non-inertial reference frames. What we said before was that in an inertial reference frame, everything would behave as expected, basically, right? Like everything would be as if you were sitting still. And in a non-inertial reference frame, that wouldn't be the case. And so this would be like I guess a special case scenario, but it happens to be Einstein, so it's worth bringing up the inertial versus non-inertial thing. So before we start, we got to have a reference frame. So we can have up, we can have down. I think for argument's sake, I'm going to be making up and down just positive and negative respectively, just to make things simple. And we can talk about the mass of this person. I'll just talk about them as a person. I'll stop referring to them as Einstein so much. And give them a mass 80.0 kilograms. We'll say that it's on Earth, so acceleration due to gravity is going to be 9.81 meters per second squared down, so negative 9.81 meters per second squared. And for this ride, we're going to say that the velocity, it's not much of a ride, the velocity is going to be 0 meters per second. And so as soon as I say that, inertial or non-inertial reference frame? Inertial. And the most boring inertial one, where you're just sitting still, right? Relative to the outside environment. And then if this thing's moving at a 0 velocity, we could say the acceleration of the system, in this case, is also going to be 0 meters per second squared. So notice that I'm distinguishing between the acceleration due to gravity and the acceleration of the entire system. And we could do a couple of quick calculations, maybe something that people might do just on autopilot. They might say mass times acceleration due to gravity, or Fg is equal to mass times lowercase g, however you like to write it, 80.0 kilograms times the negative, and when I sub in my values, I'll sub in the negative for directionality, 9.81 meters per second squared. And so that might be something that you just do without even being asked. And I haven't asked a question yet out loud, but it says at the top of the page, it says to find the normal force that would show up on the scale in each scenario. And so the normal force would be the force between the person's feet and the ground, the upward force acting on the person. And in this case, or in the case of like any time you stand on a bathroom scale, that normal force is essentially what's being read off the bathroom scale. So we're thinking about what the reading on the bathroom scale would be if this was like a bathroom scale of physics or a doctor's scale of physics that would give readouts in newtons. And I know that oftentimes you get other units on a scale, but remember, if you get units of kilograms on a scale, it doesn't really measure kilograms. It tells you how many kilograms you are, but it tells you how many kilograms you are with the assumption that you're sitting on the surface of Earth in an inertial reference frame, right? So we're looking at newtons. That would be the force that would be pushing up on this person. And I happen to have a bathroom scale that measures in newtons, but that's kind of a weird thing. Nobody buys those really, just physics teachers. It's in the cupboard over there. Anyway, so first thing we'd want to do is say what we're doing. Find the normal force. Second thing we'd want to do is draw a free body diagram. So a nice, simple free body diagram always starts out with a geometric shape, like a rectangle or a square or a circle, and the forces acting outwards on the center of mass. In this case, I've got force due to gravity acting down on the person. Now remember, we're talking about the person right now. We're not talking about the elevator or the entire system. This is just the person, and so the upward force would be a normal force acting on their feet. Truly, it's an action-reaction force. It's the force of scale on feet, and there would be a downward force of feet on scale, but we just want to talk about the normal force, okay? So separating that out. And then we'd say that picture is equal to F net for the system. I'll just call it Fnet.sys, the net force acting on the system. Now the net force acting on the system, if I wanted to tease that out as its own separate equation, I could just say, hey, Fnet for the system is going to be a Newton's second law force. We could say that's mass times the acceleration of the system. And immediately I say to myself, well, if the system's not accelerating, what's the F net on this system? 0. Yeah, I mean, if the system acceleration is 0, then the net force on the system is 0. That means the whole right-hand side of this expression here is going to be equal to 0. And remember, every time you draw a free body diagram, it's a visual representation of an equation. You know, like oftentimes just like a simple linear equation, but it's a visual for how we construct our equation. So then we take our free body diagram and we say, okay, well, F net sys is equal to, and we just say, hey, I don't have any x components to this, so this is a very simple linear equation, one-dimensional, F normal plus Fg. And you notice that as I write out the equation, I'm not subbing in positives and negatives for directionality. I'll reserve that for when I bring in my givens. Some people stylistically like to put in their negative signs when they construct the initial equation. And if you do that, you have to remember not to additionally bring in the negatives when you bring in your givens. And that's a stylistic choice. I'm going to go with this stylistic choice right now. Okay, maybe in the future, I'll think it's advantageous to put my negative signs in when I construct my equation. Anyway, I want to get the normal all by itself. And I'm going to assume that I don't already know that F net sys is 0, but I'll get F normal all by itself, and I'll get F net sys minus Fg equals F normal. And if I wanted to write that in the preferred isolated variable off to the left format, I could say F normal is equal to 0 newtons minus Fg, which we already declared was 80 times negative 9.81. Meters per second squared. And if you do the math on that one, 80 times negative 9.81 ends up being positive 784. You guys help me out with the decimal places. I want to make sure I didn't round this wrong. I get positive 784.8. Everybody agree? All right. Sweet. And then it looks like we've got 3 sig figs way back when in the givens, so we'll say it's approximately 785 newtons. And positive means up in this case. So we'll convert that back to English for ourselves. And I just want to make this statement. This is an inertial reference frame. Inertial reference frame. And really, the way we can make that kind of a claim is that it's a constant velocity. Constant velocity environment. Non-acceleration. But what that means is that this person has a normal force of 785 newtons when they're sitting still. And that should be true for all inertial reference frames. Okay? Not true for non-inertial reference frames. Anyway, I want to go back up the page here. And I want to make a claim real quick that this time the elevator does not have an acceleration of 0 meters per second squared. This time I'd like to have an acceleration to this system of 5.00 meters per second squared up. And you know, if we were telling this as a story, maybe the person gets into the elevator, they weigh themselves, they press a button, the engine engages whatever the motor is that's driving this thing, you know, like the hum, and instantly this thing accelerates. Does it accelerate for a long time or a short time? You've been in elevators. Do they accelerate from rest for a long time? Like, do they do it for like the next 10 seconds? Or do they do it for like just a very narrow window of time, the acceleration? How long does it take to get up to speed? Sure. There's a lot of people doing here, I'll put it on camera. Whoa. They're saying this much time. Not a lot of time, right? Think about it. If you're in an elevator, and when I was a kid, I probably told you this if you had me in grade 11, I used to deliver newspapers. And I would get into the elevator, and it was an old building, and so the motor didn't I don't know what the different types of motors are, different types of elevator drives are, but this one just boom, it just kicked into gear, you know? And I would feel the newspapers pull down on me really hard. It's a 1970s building. I bet you the elevator hadn't really been renewed since the 70s, right? And maybe it was 1960s. Actually, the nice thing about this place is it still exists, and the units are enormous, huge apartments. People are knocking down walls and making them into beautiful. And anyway, it doesn't matter. Condo fees are still reasonable. Anyway, I'm selling this to you. I'll buy there when I retire. Anyway, so this building I deliver papers to, I would really feel it. I would really feel this change in the normal force, but it only lasted for an instant. And then I'd go up to like the 8th floor, or the 10th floor, or whatever. And on the way, I'd be going at a constant velocity, okay? So we want to explore that as we get there. But right now, this motor just engaged, okay? Now, we're still on Earth. We're still the same person. So we say, all right, well, the acceleration is 5.00, I could say positive 5.00 meters per second squared, just translating up into math. The force due to gravity, still same. Fg is equal to negative 784.8 newtons. Remember, force due to gravity is going to be a downward vector. So I'm going to leave that in the proper negative. It hasn't changed. Same fella, same planet. And then we do ourselves a solid and do ourselves a free body diagram. Remind ourselves of what we're doing. And like I say, the force due to gravity has not changed. Make a prediction. Is the normal force increasing or decreasing if you're going to accelerate upwards? Increasing, yeah, look at this. If you're going to accelerate upwards, this force would have to be more than the downward force. That's just like a prediction based on my early days as a paperboy, okay? I love delivering in the apartment building because even in the rain or the snow, great. Also, the people in that building tipped really well. Also, at Halloween, they gave lots of chocolate. It was great. Anyway, now I'm selling you on getting a paper route, but it really actually was pretty good. Nobody gets the paper anymore. All right, so the equation, I cannot say, if I was going to make this statement again, F net sys equals mass times acceleration of the system, I cannot say that that zeroes out because the acceleration is no longer zero. Okay? I'm just saying it out loud. But the equation does remain the same. F net sys still equals F normal plus Fg. The isolation still works. I'll just write it like this time because it's the same thing I'm doing again. F normal is still equal to F net sys minus Fg. But when I sub in my values, F net for this system is going to be the mass of the system, which is just the person in this case, times the acceleration of the system, minus mass of the system times the acceleration due to gravity. And the math person in me really wants to factor that mass out, but I'm not gonna. 80 kilograms times 5 meters per second. Notice positive 5 meters per second squared. I know I'm dropping off the zeros because I'm trying to squish it all in here. Minus, and I'm just going to write it in as the minus negative 784.8. That's the unrounded value for gravity. Oh, and I got to make sure there's a negative in there because it was negative. So it's going to be a plusive. So head math, 80 times 5 is, starts with an F. 400. 400 plus 784.8. Anybody do it in your head? 1184.8. Yeah? So, and obviously it's positive, so we know that that's up, but we could also round it off to 3 sig figs, which feels a little bit dirty at this point, but it's going to be, 1,180 newtons up, or 1.18 times 10 to the power of 3 newtons up, either one. If you wanted to be less ambiguous about your rounding. But pause and say, is this inertial or non-inertial? Non-inertial. And so when I look at this, I say, oh, the reading on the scale is not what you would expect in an inertial reference frame. It's been modified because it's a non-inertial reference frame. So we say non-inertial. Accelerating. Fair enough. All right. So carrying on with this idea of the elevator ride, I say, okay, once we do get up to speed, we're going to say that we some people say coast, but we move along, it's like cruise control. We move along with an acceleration of 0 meters per second squared. But let's just say that this elevator is able to get up to, in fairly short order, a speed of 10.0 meters per second up. Still on Earth, same fella, same elevator ride, negative 784.8 newtons per FG. Myself that little construction line. Find the normal force. And again, we still do our free body diagram. Now, somebody predict for me, based on there being a constant velocity, how would the normal force and the FG compare? Jake, what do you say?
Sorry, how would you compare?
Yeah. Somebody help him out. Come on. Yep. Same. Yep. So we're going to say, sorry, Jake. I saw you. You're looking intensely, but it's morning, so you're half asleep probably. It's fine. I am too. All right, so we've got our FG, we've got our F normal, and the prediction is that they should be the same if you're moving at a constant velocity. Okay? So we say, oops, here I am trying to be all good about my color coding. F net sys. And again, maybe I could just say it out loud. What's the value of F net system based on our givens? Got a few people doing the circle, the 0, right? Okay. So this guy is going to end up being 0 for the same reason as it was 0 before. There's 0 because the acceleration is 0. And I think I'm going to shortcut myself a little bit. I'm going to say, hey, look, I could do this, but this is getting repetitive. F normal equals F net sys minus FG. We just declared that the F net sys is equal to 0. And so F normal is going to end up being negative of negative 784.8 newtons, or 784.8 newtons, or approximately 785 newtons up. And again, we can make this claim. Inertial reference frame. And it doesn't surprise anybody that if we're going at constant velocity, you'll have the same weight on the scale as if you were sitting still. And it shouldn't surprise us that the scale has to push up extra hard during the phase when you're accelerating, getting up to speed, right? So yeah, there's going to be a little bit of a jump in the scale measurement, which means you should never weigh yourself on a diet while you're in accelerating elevators. But that's a very niche scenario, I suppose, right? All right. So in this situation, one more time, if this was like a reasonable elevator ride, and I were to make the claim acceleration equals 0 near the end of the ride, what direction would the acceleration probably be near the end of the ride? Yep. Down. Yeah, absolutely. So we say, all right, the acceleration is going to be, I could just say 5 meters per second squared down, or I'm just going to jump to negative 5.00 meters per second squared. Same force due to gravity. And I chose 5 again on purpose. It's going to be a little bit of pattern recognition here. So find the normal force. And if we throw in a free body diagram, I'm just going to make the out loud prediction that if FG stays the same and I'm slowing to a stop, then whatever that normal is, and maybe I'm over exaggerating the size of things here, it's going to be less in magnitude than the FG, so that my F net for my system is going to be a negative value overall. But again, I'll have the exact same formula as we had once before. F normal, once I isolate for F normal, it'll be F net sys minus FG. I sub in my values just like I did in the second column over. Mass times the acceleration of the system minus mass times acceleration due to gravity. This time, I end up getting 80 times negative 5 rather than 80 times 5 because this time the acceleration is downwards rather than upwards. So I'll end up getting negative 400 newtons, right? 80 times negative 5, negative 400 newtons, minus negative of negative 784.5 newtons. All those negatives are important. But then we end up getting positive 384.5. Not 5, it's 8, isn't it? 784.8. 384.8 newtons, or 3 sig figs, 385 newtons up. And as I get to the top of my elevator ride, I know, and when my kids were small or when I take them on elevator rides, when you get to the top of the elevator, you know, like if they were visiting their Nana or something, they would get little butterflies. And while you have a diminished normal force now at the top of the elevator ride, when the fluids inside your body cavities have a diminished normal force, that gives you a little funny sensation. It's going to make you feel like you have little butterflies in your tummy, and it's kind of thrilling. It's also why, you know, when we have accelerations of this sort, when we go to Canada's Wonderland or, you know, like any kind of amusement park, why we, you know, have those funny feelings in our stomachs, you know? So again, though, this is a non-inertial reference frame. Which means it's accelerating. And actually, you know, here I've got like regular normal force. I hate to say normal force. I have a regular inertial normal force. I have an inertial normal force. I have two non-inertial normal forces, one where it's increased, one where it's decreased. And I like to go to the extremes. So in the extreme, what would happen, or how would it have to be the case? I'll just like carve out a little bit of real estate for myself here. What would have to be the case for the normal force to actually be equal to 0? So I want to set that out. I want to say, hey, if the normal force was going to be equal to 0, I'll take this same equation that I've been sort of playing with here and just play with it a little bit more and say, okay, well, if that F normal equals, I'll just call it F net minus FG, if the F normal was equal to 0, what would have to be true about the scenario? Now, I could take that FG back over to the other side. I could say, okay, well, F net would be equal to FG. That means that the mass times the acceleration of the system equals the mass times the acceleration due to gravity. Mass is going to cancel out. What am I really saying here? If the normal was going to be equal to 0, if you were going to have like a true feeling of apparent weightlessness, and that's what it means to have a normal force equal to 0, what's really happening? What's the physical scenario? Yeah?
Like the acceleration of the system is 9.81.
Yeah. That's it. The acceleration of the system is 9.81. And then physically, what must have happened to your elevator? What do you think? Yeah? It's falling. Yeah, somebody snapped that cable, right? Like somebody came along and cut the cable. Now, if you look in your workbooks, I think that there's some comment somewhere along in there about the safety mechanisms for elevators. It turns out there are braking mechanisms if it accelerates downwards at such and such a rate. Like there's all kinds of things like that. You can imagine early elevators didn't have that kind of stuff, and maybe there's like some nightmare story in New York City about somebody plummeting to their death or whatever. Well, that doesn't really happen anymore because these braking mechanisms really do kick in. Yeah. Yes, of course. Okay. What about this? What if I was in an elevator? Here's my elevator. This isn't the person anymore. What would have to be true for me to be in an elevator and standing on the ceiling? What then? Yep. Yeah, have to be accelerating downwards at some rate higher than gravity. And so like we could say, hey, if I put like a rocket on the bottom, this is a rocket, this isn't somebody's feet on fire, but if you had a rocket on the bottom of this elevator and it was accelerating downwards, I bet you we could even figure out what the normal for, or how to do this. I bet you, and you could probably figure this one out. Think of this as an exercise. If we know that this person would be on the ceiling, don't we know that the normal force would be acting downwards? And we'd have to be in a situation where, if this was the free body diagram, we'd have an FG going this way. True? Wouldn't we also have to have a normal force going which way? Also downwards? Does that make sense? Like that? We're going to have to figure out what kind of acceleration this person would have to have in order for their feet to stick to the ground. Do you think we could even accelerate at a rate where they could feel like they're just standing on level ground? Could we accelerate to the point where whatever normal force they feel on their feet, while actually upside down, is the same as 784.8 newtons? That would be kind of wild. That would be something where they wouldn't know until they hit the ground, like what was happening. Like they wouldn't, can we agree that they would actually feel like they were sitting still? I want you to see if you can figure that one out. I'm going to leave it as a head scratcher for you. Figure out how fast they would have to be accelerating in order to feel like they were just sitting still, but actually they're plummeting to the bottom of an elevator shaft at ridiculous speeds, okay? I'll stop recording there, and I want you guys to take 2 minutes, figure it out. Go.